t-test is just a special case of ANOVA in which you have only two groups. All right, back to the ANOVA. Let's fill those values in. While we're at it, give some thought to the degrees of freedom for your error term. Recall that it's n minus k. Carrying on the discussion that we started on the last slide, if you had only two groups, k equals 2. So if you had only two groups, the degrees of freedom would be the n of the first group plus the n of the second group minus 2, which is the denominator of the pooled variance. Given that the mean square for the error term is equal to the sum of squares for the error term divided by the degrees of freedom for the error term, your mean square error in the independent group's ANOVA is pooled variance. But I digress. Dividing mean square treatment by mean square error, you will find that the F ratio is 1.00. An F ratio of 1.00 is just about as non-significant as you can get. Recall that our goal in testing the omnibus F ratio is to evaluate whether or not F is significantly larger than 1. Nonetheless, we went to the trouble of looking up a critical value of F. We might as well compare our observed value to it. Because F obtained is less than F critical, we should fail to reject the null hypothesis. Our eta square would be the sum of squares for the treatment divided by the sum of squares for the total. This value tells us that approximately 5.08% of the variance within the dependent variable is due to the independent variable. So, no treatment effect? That's disappointing. But is it really the case that we can say that there is definitively no effect of treatment? Or is it just the case that the treatment is overwhelmed by the subject variance? In other words, if we remove the systematic variance from the model, are we left with a statistically significant prediction of the treatment effect? Okay, let's analyze this data the way we should have approached it in the first place, using a dependent group's ANOVA. Our first step is the same as it was for the independent group's ANOVA. We're interested in seeing whether or not at least one pair of means differ from each other. The design notes that you controlled for relevant demographic variables within each of your blocks. Thus, this is a dependent group's design, more specifically, a randomized blocks design. Note, of course, that a randomized blocks ANOVA and a repeated measures ANOVA are mathematically identical. They differ only in the underlying methodology that you followed in collecting the data. But as was the case with the dependent group's t-test, repeated measures analyses tend to be more powerful due to the fact that they result in better matching between groups. We'll gloss over the assumptions again, but remember, you need to be thinking about your assumptions when you're collecting your data, particularly the assumption of independent random sampling. If you collect your data in such a way as to create pockets of dependency within your data, all of your empirical data gathering will have been for naught. There isn't much you can do to correct things after the fact. The assumptions of normality and circularity are less critical, and they're easily tested in R. So for now, we'll just assume that they're not problematic. This step is also the same as our third step in the testing of independent groups ANOVA designs. The key difference here, though, is that the degrees of freedom for the error term is markedly less than the degrees of freedom for the independent groups ANOVA. As we've discussed, the power of an analysis generally decreases as the degrees of freedom decreases. Thus, in a direct parallel to the dependent group's t-test, the dependent group's ANOVA will only be more powerful than the independent group's ANOVA if the subject variance that is removed reduces the unsystematic error term to a sufficient degree as to compensate for the reduction in power associated with the lower degrees of freedom. In the present example, the F critical that we are using is exactly the same between the two analyses. But this is only because there is no row for a denominator degrees of freedom of 42, and so we dropped down to the same degrees of freedom value that we used for the independent groups analysis. The sum of squares for the treatment effect is similarly identical, owing to the fact that we did not partition the treatment variance any further for the dependent group's design. The blocking factor is of paramount importance in this design, though. This is the whole reason we undertook to control for subject characteristics, to come up with an estimate of the subject variance that we can subtract from the unsystematic error variance of the independent groups ANOVA, so that we can reduce the amount of unsystematic error variance that forms the denominator of our F ratio. The sum of squares for the blocking factor is calculated exactly the same way as the treatment sum of squares, except that it involves looking at the block means instead of the treatment means. Per the equation on this slide, we're looking at the squared difference for each of our 15 block means, weighted by the n size of each of our blocks. We're going to need the sum of squares for the error term if we're going to successfully calculate an F ratio for our treatment effect. But first, let's figure out what the total sum of squares will be. Well, consider that the treatment effect involves evaluating the variability amongst each of the treatment means, and its numerator can be defined as the sum of the squared deviations of the treatment means about the grand mean. The numerator for the total variability, therefore, should be equal to the sum of the squared deviations of each individual data value about the grand mean. This formula should look really familiar. It's the numerator for the variance equation. Thus, this suggests a shortcut for the calculation of the total sums of squares. If you rearrange the formula for variance, you can see that the total sum of squares is equal to n minus 1 multiplied by the variance of all your data points. Ultimately, you can use either the top formula or the bottom formula. But given that the bottom formula can be derived with one of the buttons on your calculator, you really should avail yourself of this shortcut. Not to mention the fact that this would remove the temptation to engage in extra rounding, as this can rapidly move your answer out of an acceptable answer range. I calculated the variance of all 60 data points to be 15.94. Thus, the total sums of squares is equal to 60 minus 1 multiplied by 15.94, giving us 940.46. We can now calculate the sum of squares for the error term to be 940.46 minus 47.74 minus 821.4, which gives us 71.32. Let's go ahead and fill in the rest of the ANOVA summary table. Now that we've pulled all of that systematic error out of the error term, our F ratio is markedly improved. Comparing this new and improved F ratio to our critical value of F, we see that the omnibus F ratio is statistically significant. We will reject HO and conclude that at least one pair of means differ. And we should now calculate eta square, which is calculated as the sum of squares for treatment divided by the total sum of squares. Wait a minute, that's exactly the same as the eta square for the independent groups ANOVA. How is it that the effect is now statistically significant, but the effect size is the same? Shouldn't this change more? Well, before I answer that, consider what the eta square calculation is doing. It's evaluating the proportion of variance that is accounted for by the treatment sum of squares within the total sum of squares. A total sum of squares that includes both the systematic error term and the unsystematic error term. If we want to evaluate the percentage of variance that is accounted for by the treatment effect after controlling the subject variance that you removed from your design, you should calculate a partial eta square. The primary difference between these two effect size estimates is that the partial eta square does not include the sum of squares for the blocking factor. It is, therefore, a fair bit larger than our original eta square estimate. Finally, we can use Tukey's HSD to identify where the mean differences lie. It proceeds in exactly the same fashion as our follow-up to the independent groups ANOVA. Through this process, we identify that the critical difference is 1.28, and that the mean of group D is significantly different from all of the other means, with no other differences demonstrating statistical significance.